It's definitely an honor to be here today to present this topic to you. We already had an introduction here, but maybe the only thing that I'll add is basically over the years at Nuvation Energy, I've really had the privilege of working on software at a number of different levels through our product. And one of the things that I think is really cool about this job is that we get to solve challenging real-world problems related to energy and use some pretty cool software to do that. So that kind of keeps us coming back, and you know, in our own way, we can make the world a better place. This is part 3 or tutorial number 3 and the last of the 3 in this series that we're presenting. And it's also the last Plug Volt seminar we're doing this year. So thanks for hanging out with us. We hope you all stay healthy and you have a great holiday season, and we're looking forward to doing some more of these next year. And I'd like to start out today with a question. Why do we care about state of health? And I think if you think over 2020 and just some of the new circumstances we've been put into, I'm sure all of you have been using portable electronic battery-powered devices even more than in previous years, you know, whether that's a cell phone or a laptop or a tablet. And if you think back, there's probably an experience you've had somewhere this year where your battery was reported at maybe 10 or 20% state of charge left, and then suddenly, boom, your device shut off. And this is certainly an inconvenience and an annoyance, but it's also a pretty good example of one type of state of health problem. Basically, you know, your batteries, they lose their performance with age and use, and they start to require more charging. They don't last as long. And the other thing that happens is it actually gets more difficult to predict what's going on inside the battery. So state of charge is less accurate. Now that's just a small example, but this can actually become a much bigger problem when you think about really big batteries. So imagine now a multi-megawatt hour battery, and maybe the application is demand charge management. And the way demand charges work on your electricity bill is that basically the utility looks at your entire 30-month period, and you get special charges for the peak 15-minute power usage across that whole month, you know, in the peak time of day. And so people install batteries to help reduce that. And if your battery for that application suddenly shut off, that could actually be a pretty expensive hit on your monthly electricity bill. And this is going to vary a lot, you know, based on where you are, but we just crunched some numbers based on some typical examples we've seen. And the cost of that, oops, would very easily be $10 to $20 per kilowatt hour of power, you know, coming out of your ESS. So you have a 1 megawatt ESS there. This could be a $10,000 or $20,000 oops. And one way I like to look at state of health is something that enables better decisions. And this happens really across all levels of the problem. We can look at the BMS, and the BMS uses state of health to do better estimation of charge, to manage charge and maybe balancing activities more efficiently. The EMS actually is going to rely on some state of health, most likely coming from the BMS, to actually have a good sense of how much energy is remaining and how it should divert the power flows around. So going back to that demand charge management example, if we had a good sense of how much energy was really in the tank, we could make intelligent decisions about how to use it to avoid those kinds of outages. And there's a third example, which is maybe a little more of a stretch goal, but we see this becoming more important in the future, and we'll touch on it briefly right at the end. I think there is an economic aspect to SOH. It's easy to ignore in the early years of an energy storage system, but as time sets in and you're faced with decisions around what do I do as the system degrades, having a good sense of state of health can help you make good decisions about how to either augment, replace, or repurpose your energy storage system. So here's what we'll cover today. I'll do a quick overview of Nuvation Energy, but I want to then dive right into a definition for state of health that we can work with. And then I'd like to look at two perspectives on batteries and state of health from those perspectives. We'll look at an external one where we have a human analogy, and that's going to help introduce the concepts of power and energy, and then we'll dive a bit deeper and start to look at what's actually happening inside the battery cell. So many of you already know quite a bit about us because this is part 3 of the series, so I will keep it brief. Basically, our roots are in engineering design services. That's where we started out many years ago. We focus on solving problems for our clients, and we've developed things that get deployed into environments that are as diverse as, you know, the ocean, the bottom of the ocean, or out into space on satellites. And in 2008, we really started developing this focus on productized BMS solutions. Nuvation Energy was launched out of that. And our vision has really been to create highly configurable BMS products that help our customers succeed with their battery systems. Today, we have over 130 installations worldwide using our BMS hardware and software, and that's growing every week and every month. And across all of these projects, if you were to look at them, we actually have a considerable variation of battery chemistry, size, and topology. And it's actually our unique configurable approach to battery management that enables us to work across all these applications. So, what is state of health anyway? If I say this battery has a state of health of 80%, what does that mean? Does that mean that there's 80% of the useful life remaining? Or does that mean that the battery is performing at a level of about 80% of a new battery? This is actually a pretty fundamental question, but we see it still becoming a point of confusion in the industry. So this is an area where even just a dictionary definition of health can help us out. According to the Oxford English Dictionary, health is defined as the state of being free from illness or injury. So health is fundamentally a statement about today. It's not a statement about the future. And when we come to battery systems, it's actually the same thing. Battery SOH is about how your battery is performing today, not about predicting how long it will last or how it will perform in the future. Another very important clarification is that state of health, health isn't the same as age. Basically, you could be young, generally healthy, but injured, and as a result of that, you know, you'd be forced to be inactive for a period of time. But you could also be old and very active. And it's the same with batteries. You could have a new battery that has been physically damaged in some way, and therefore it's not performing. You could have a battery that's many years old, but it's doing its job still because it's been well cared for. And if we take the human example of health even further, things get even more complicated when you visit your doctor and you ask, well, how healthy am I? There's all sorts of metrics we could pull out for this. Maybe pulse, blood pressure, body mass index, resting heart rate. I'm not even getting into, you know, all the blood tests and the cholesterol levels, but all of these things have numbers associated with them, and it can actually be quite overwhelming. Can we really come up with a single number that describes how healthy I am as a human being? We actually have very similar challenges when it comes to batteries. We could ask the same question, how healthy is my battery? And we could get a multitude of answers, all with scientific numbers behind them. Some of them might be something like cell capacity, cell impedance, cycle count, total throughput, but the list really could go on and on. These are all numbers, but is it possible to account for battery degradation in some single comprehensive number? And what really helps here is if we recall really fundamentally what a battery is about. What is its fundamental function? And it really is to store and release charge. A single battery cell, that's what it does. That's how we think about it. And while all the very many health metrics factor into how it performs at this function in some way, I think it does make sense that our definition of SOH must be grounded around this fundamental function. And so what we've shown here in this equation is what I would say probably is the most common definition of SOH for a battery at the cell level. And how you get this is you actually look at the actual capacity, the amount of charge that you can store in the battery today. And if you were had a BMS with readings like this, one way you could get that is basically by doing a really deep discharge down to 100% DOD. You know, when that gets to the bottom, you look at the number of amp hours, that's basically a capacity test. And then what you would do is you would divide that number by the nameplate capacity. That's what comes from the battery manufacturer, and then multiply all that by 100%, and that gives you your state of health based on the amp hour capacity. So it's pretty simple. If your state of health is 50% and your nameplate capacity was 50 amp hours, your actual capacity of charge that you could store in the battery would be 25. And this is a great definition for the lab. It's great when you're thinking about batteries as battery cells, but in the real world, when we actually want to use that charge, the battery is always connected to some kind of power conversion equipment. And most often, especially in stationary, we're connecting to inverters because we're converting DC power into AC power. It is becoming more common to see DC to DC converters as well. But basically, once you go through that conversion process, you're no longer thinking in terms of charge, you're actually thinking in terms of power and energy. And you probably have seen a utility meter on your own home or in the area where you live. And if you think about what's on that meter, it's not measuring the charge, it's actually measuring the power flow, the kilowatt hours that are being used. So there's a great quote by Peter Drucker, which is, if you can't measure it, you can't improve it. And really, the bottom line in energy storage is about optimizing and improving and managing energy and the kilowatt hours that we can get out of a battery. So does it not make sense that for an energy storage system, we should somehow tie our definition of state of health back to that fundamental function? Let's think about batteries and let's look at what energy would mean for a battery. And we'll do that from an external perspective. I'm just going to look at a battery largely as a black box that delivers energy. And to do this, I'd like to bring in a human analogy, because as I was thinking about all of this, I realized that energy storage systems are actually a lot like trained endurance athletes. And in this particular analogy, I'm going to draw on some of my own hobbies and interests in the form of cycling. I've done some racing myself, and I certainly enjoy riding my bike a lot. And one of the things that has really changed how cycling is done scientifically today is the advent of the bicycle power meter. And this is something that you'll see a lot of serious cyclists using these days. It's definitely used by most professional level cyclists, and coaches and athletes use these power numbers, basically wattage numbers from their rides, to measure their performance and, track their training and plan their workouts. And one of the reasons this is so effective is because power and energy, those are very closely correlated to performance. And cycling is actually largely an energy management activity. Once you are riding, you have to manage your energy carefully if this ride is going to last more than a few seconds. So let's look at power on a bike. What does that look like? Well, this is mechanical power because you're turning the cranks around and around. And generally the way we define that is work divided by time. And this mechanical work is a force over a displacement. So that's commonly Newton meters as the unit. And then that's over a certain amount of time, which is seconds. That then is equivalent to 1 joule per second, which would then get us to watts. And if you think about pedaling, basically, if you're pedaling faster or you're pedaling with more force, you are then doing more work and you're generating more power. Now, this is great, but if you're going to go on a ride, a long ride, or you're going to compete in a race, that power is really only going to make a difference if you can sustain it for a long enough period. And this is really where our concept of energy comes in. Energy is simply power times time. So if we want to look at it from the joule per second perspective, we'd multiply that by time in seconds, divide it by 1,000, and that would get us to energy in kilojoules. And most often, athletes will be looking at kilojoules. This is kind of the unit that they think about in terms of energy. That's also something that could easily be converted to calories. If you've looked at like those digital readouts on a spin bike or a cycling computer, you'll see these numbers, you know, at the end of your workout or your ride. But unless there's actually a power meter on the bike, they're pretty rough estimates, so they're not very accurate. But once you have a power meter, these actually become pretty exact. In the case of the battery, everything is nearly the same, except that our units are going to be a little different. So electrical power in watts is voltage times current. That's volts times amps. And energy from a battery, kilowatt hours, is simply power times time again. And this time it's the watt second, and we divide by 1,000, and that gets us to kilowatt hours. So now that we've oriented ourselves with power and energy, it's actually really important to understand a key distinction that we need to make in energy storage system design, and that really is power versus duration. This concept actually applies pretty well to batteries and to different cycling disciplines, as I'm about to illustrate. And in the battery world, a common way to communicate really a combined discharge duration with a rate together is actually through the C rating of the design. And what I've shown in this table is some different battery applications with different C ratings, you know, 10, 4, 1, 0.25, 0.1. I've showed what that corresponds to in time, and I've just given some examples. Yes, I'm doing a little bit of cycling geek out here, but these are some different races that actually kind of correspond roughly to those time durations. And what's neat is really this whole table is anchored by this central row that is actually the 1 hour duration. And this is actually a pretty important time for most cyclists that are training. It's like your 1 hour time trial. And what you do is you go out there, you put everything down, you ride as hard as you can, but you try to pace well for 1 hour, and then you're totally depleted. And that's exactly the same concept as what we would talk about with a 1C battery. So with a 1C battery application, we actually have a discharge current in amps that's the same as the battery capacity in amp hours. So if it's a 100 amp hour battery cell, we'd have a 100 amp discharge current, and that would take 1 hour to deplete. So the key thing is there's many different cycling disciplines, there's many different battery applications. As you get above the 1C rate, the current and the power goes up, the duration goes down, and as you get below it, the duration goes up and the power goes down. And athletes, they train specifically for these specific event durations. Battery systems have to be designed for the end application in mind. A 10C design is going to look very different from a 0.1C design. And just to help illustrate a little bit of this visually, let's look quickly here at a design that's tilted more towards the power end of the spectrum. And this design is actually something from one of our partners called Spears New Technologies. It's a pretty cool Second Life application. But what I want to draw attention to is really just the relative size of these battery modules compared to the bus bar in the interconnect. So these modules, you know, if you're used to looking at 18650s, they may look pretty large, but in the scheme of how big things can get for stationary energy storage, I'd say they're moderate to maybe even in some cases on the small side. And there's actually pretty beefy bus bar connecting all these together. So that's just what I want to highlight, is the ratio of those two sizes. This is a power design. And if we were to go and look at a cycling discipline that's tilted, towards the power end of the spectrum, track cycling is a great example of that. These races are usually only minutes long, definitely much under an hour. You'll generally see these cyclists, they tend to look a little more built, bigger legs, bigger arms. But if we go back to the other end of the spectrum, we think about design for endurance. What I've got here in the photo on the right is actually an example of a solar plus storage project we helped out with on an island. These are massive cells. They're, I think, 1,000 amp hour, if I recall correctly. And if you look at the connections between these, there's actually no bus bar. These are almost like little segments of booster cable pulling everything together. So you are not going to be pushing 1,000 plus amps through these interconnects. In fact, this system is designed to operate at a much lower power level, but its fundamental function is to last many hours. So if we were to go over to a road racing type of athlete, somebody who has to put out the power for many hours, they're actually going to look a little different than a track cyclist. Going to be a leaner build, skinnier arms, skinnier legs. And they're going to train for that endurance. There's a pretty good reason why you don't see anyone winning the Tour de France looking like a bodybuilder. So now that we've looked at the power and the duration, or the time aspect of energy output, let's look at what are some of the limiting factors in total energy output. First, for the athlete as our analogy, and then we'll apply that to a battery system. One of the most important factors, if you're going to ride your bike and get through some specific event duration, is actually your pacing. So unless your race is merely measured in seconds, you're never going to be pedaling as hard as you possibly can. You're going to be pacing at a power level that you can sustain for the correct duration. So you're generally not getting anywhere close to what your maximum power could theoretically be. And what that means then is, once you've established this pace, you do have to train to be able to do that. The limiting factor for you is really going to be endurance, and that's limited by basically the energy stores in your body. Your body is an energy storage system, and two examples of how we store energy are our glycogen reserves and also our fat. And so endurance athletes that want to, push a certain power for a certain amount of time, they're actually going to be training to increase the amount that they can store in their body so that they can finish their event. So let's assume now, you're fully trained, you're ready to race, and now you stop training. What happens? Well, probably one of the first things is your endurance is going to start to go down. You'll maybe be able to maintain your power that you've been practicing, but instead of 2 hours, maybe it'll be 1 hour, 45 minutes, maybe it'll be 1 hour at some point. And that also means that your total energy output is shrinking as you're able to put out power, but only for less time. Another way that you'd lose fitness is actually through power loss. So if you're not practicing your pacing, if you're not training at that race pace, over time it'll be harder and harder for you to actually even sustain that power level, even if you had a lot of endurance, to go slower for a long period of time. And so what happens is your total energy output decreases, and this happens along two dimensions. There's a power loss aspect to this, and there's an endurance loss aspect to this. And what we'll see is it's really identical for energy storage systems. Let's think about what limits an energy storage system. you have a specific rated power on your design, it's quite common that an ESS is rated at a power that is actually, below what the cells are maximally able to deliver. And the reason for that is actually tied back to those examples that we looked at. If you think about what's inside an energy storage system, well, you've got the bus bar, you've got the switch gear, you do have the cells, but there's all these things that hook it together and make it a system, and the current has to flow through those. So all of those things are rated for a certain power level, and those are chosen based on the application. So basically at the top end, we are current limited in our designs. And the BMS also plays a role in this because the BMS serves the pacing function, just like in the race, the athlete has to pace. So basically at the top end, you will max out on a fixed current based on your design and your BMS configuration. On the other axes, we have our rated capacity, and that is really just fundamentally a function of the battery's ability to store charge. So regardless of the power level of the system, you're really going to be limited by how much charge you can pull out of those batteries. So what happens? This is a new system, a fresh one. What happens when this degrades? Well, one of the first things you'll notice likely is capacity fade. The battery just won't last as long. You can't store as much charge in it. But there's actually a more subtle but still important effect that happens as well, and that's called power fade. And what's actually happening here, recall that power is voltage times current, and if we're going to use the battery system at its design maximum current, what's actually happening in the battery is it's not able to deliver that same voltage even though you're at the maximum current. And as a result, the power droops, the voltage droops and the power droops because voltage times current is power. And that power loss, it doesn't just disappear, it goes into heat. And the net result is your total battery energy output, it goes down. And it also goes down in two directions. You have the capacity fade component, which is usually the most significant, and you have the power fade component, which depends more on the application. So let's take this back to our state of health formula. What can we do with this now? Well, we can make a simple but subtle shift where basically we replace the actual capacity. Instead of using amp hours, we use kilowatt hours, and we take the nameplate capacity, and instead of using amp hours, we use kilowatt hours. And what we're doing now is we are rating the system based on its ability to deliver energy, which is really what we care about in our end application. So this is more complex to estimate, but a cool side effect of this is, there's a lot of power meters out there. You can do a test and you can get a read on what this SOH rating is for a battery system by actually doing a field test. And the one other thing I will point out is what we've seen is some people try to estimate this by actually basically taking the SOH of the battery that's calculated from amp hours, and then they try to multiply it by the nameplate capacity. But of course, that's actually not the same as doing this because you're more or less ignoring power fade in that case. So you actually get two different numbers. So now that we've set up power and energy and the concept of power fade, let's shift to the internal perspective and dig a little deeper to look at what's going on inside the battery. What's in a battery? Well, the answer to this question is going to depend on who you ask. Is it a chemical engineer giving you the answer, or is it an electrical engineer giving you the answer? If you ask a chemical engineer what's in a battery, you'll get four major components: the anode, the cathode, the separator, the electrolyte. And this actually reflects the physical composition of the battery cell itself. If you were to go and cut this battery open and look inside, these are the components that you would find. But please don't try this at home, it's a bad idea. We'll just work with diagrams. And this is the part where I have to very briefly take off my electrical engineering hat and temporarily pretend I'm a chemical engineer. It's out of my comfort zone, so we're going to keep this really high level. But at a high level, what's happening here is really just ions are flowing around in different directions. And if you're charging a battery, the positive lithium ions, they flow from the cathode to the anode, and they go through the electrolyte. So that would be in the right to left direction here. And the electrons, they actually flow in that same direction, but they go through the circuit and then they recombine at the anode. If you discharge, the same process happens, but you flip it around and go in the other direction. So if we were to ask an electrical engineer what's in a battery, we'd actually get a very different answer. We'd hear about 3 kinds of circuit elements that are in a battery. There'd be a voltage source, and there'd be a bunch of different resistors and capacitors. And this doesn't actually correspond to what's inside the battery. It's really a way to model the voltage and the current behavior that's observed here at the battery terminals. You can think of it as an electrical engineering analogy. And now that I'm able to put my electrical engineering hat back on, I'm already feeling much better. In this model, the resistors and the capacitors, they are used to represent the dynamic response of the battery to current. So basically, if your battery is completely at rest, it's been sitting there for a long period of time, these don't contribute anything. The voltage across that is 0. But as you start to use the battery, charge it and discharge it, and maybe change direction of current flow, these actually become a fairly significant part of the terminal voltage. The internal circuit voltage source is actually used to represent the internal potential in the battery, and that's related to the state of charge. That changes as the battery is charged and discharged. What makes this circuit more complex than it initially looks is really just the fact that none of these elements are actually fixed parameter values. They all change with time, and they all change with conditions. So let's look at the open circuit voltage curve a little bit. The example I have here is for an LFP battery. And what you can see right away is if you charge the battery, this voltage goes up. If you discharge it, the voltage goes down. And so that's a function of state of charge. And the shape of this curve and the slope, they depend very heavily on the battery chemistry. Even within lithium ion batteries, this can change significantly. And it's really this change in voltage over state of charge that causes the output power of a battery to change, even when you're at a constant current. So this is just a function of the chemistry. So no real battery can generally deliver constant power as it's being discharged. And what about these resistor and capacitor parameters? Well, if we look at these in more detail, this is where things actually start to get pretty interesting. So these RC components, they actually vary very significantly with both state of charge and temperature. And what we're looking at here is, you can think of it as like a combination of all the resistance elements, just to make the illustration simple. But at this point in the back, we're down maybe around 4K microohms. At this point in the front, we're way up near 12. So that's like a factor of 3 change. And that's just over this operating window, which is large, but not incredibly large. So this actually has a pretty significant effect on terminal voltage, especially as you push into the corners of this surface. And obviously, as the current goes up, this is going to affect the voltage even more. And I would like to actually mention the methodology that came from here, or that we used to create this. It's actually based on a joint paper we did with University of Waterloo. And we came up with a way to basically conduct a set of experiments very efficiently that would help you model these parameter surfaces for a given battery cell. And that's something that we've used for some customers and some battery manufacturers as part of the cell modeling process. So the link is in here, and when you get the presentation after, feel free to check it out if you're interested. Now that we've set up some of the internals of a battery, we have an equivalent circuit we can talk about. Let's look briefly at degradation. What are some of the culprits for this? I like to break it down into three. There's time, there's use, and there's abuse. And we're not really thinking too much about abuse here today. We're assuming basically that you're using a good BMS that's going to prevent most of the abuse, and you've set up your application correctly. Even if you're taking very good care of your cells, eventually they're going to reach a point in time where they're at end of chemical life, or they're going to continue to degrade with normal use to a point where you can't use them. So the degradation is going to get you one way or another. It's really just a matter of speed. And when we talk about degradation, probably a lot of you have heard some terms like lithium ion plating thrown around, things like that. But there's actually a ton of different mechanisms that can cause a battery to degrade internally. And they can apply to the anode, the cathode, the electrolyte, the separator. There's lots of PhDs working on this and constantly researching this to understand it better. And what I wanted to show was really just a quick, more of a visual overview of just the scale of the number of effects that we can see here. And we've lifted this from a pretty neat master's thesis that was done a few years back at the University of Waterloo. You can take a look at the original one if you're interested. But basically, I don't want you to read this and get eye strain. I just want to point out the fact that this is just the anode. They identified 12 different degradation mechanisms. What was cool though is they linked those to only 3 different impacts on performance: power fade, capacity fade, and Coulombic efficiency fade. When we look at the cathode, there were 9 mechanisms, but only 2 impacts to performance: power fade and capacity fade. And when we look at the electrolyte and the separator, another 5 mechanisms, but again, the same 3 impacts here. So what can we conclude from this? Well, we saw 26 different degradation mechanisms identified, but the reality is only a few of these, only a few impacts to the ESS performance are things we really need to care about. The most significant ones are actually capacity fade and power fade. We're not talking about the Coulombic efficiency fade today. That is another effect and a smaller factor, but it doesn't, given how we've defined state of health right now, it doesn't really fit into it. The cool thing about this is the equivalent circuit model can actually help us represent both of these major effects. And I think the best way to make that evident will be through some examples. So first of all, looking at just a circuit diagram, how do we represent power fade? It's basically an increase in one or more of these resistances. So as the resistances go up, you have current flowing in here, there'll be more voltage drop across these resistors, more thermal energy dissipated there, and you won't have as large of a terminal voltage as you're discharging. And then capacity fade, that actually affects the curve that's used to model that internal voltage source. So that curve will actually shrink. So we like doing experiments. We took a bunch of LFP cells into the lab. We found some eager PhD students and co-op students, and we ran a bunch of experiments. And these experiments were on some 20 amp hour LFP cells, and they had been degraded through a number of different mechanisms, but largely accelerated aging type techniques. And so the graphs we're going to show are comparing two different cells that in this case happen to be relatively high SOH, around 92%, and relatively low SOH, around 65%. And that SOH was calculated not based on energy, just based on the pure amp hour capacity. And that's because we're thinking of it as a battery cell. It's what we do in the lab. This is an important point where, since this is 2020, I do have to make the obligatory COVID-19 health and safety plug that proper COVID-19 health and safety procedures were followed during all lab work. The only health impact here was on the battery cells. What did we find? Well, we ran the design of experiments methodology, that we showed you earlier to get these surfaces. We did it on a fresh cell and on an aged cell. And you can see the fresh one at the bottom here, the blue, and the aged in the red. And right away, you'll see that this surface has moved up, from maybe 10K roughly to over 15K at this point. That movement upwards represents power fade because the resistance has increased. And not only has it moved up, the shape has changed. So the degree of power fade at different conditions is different. The other thing we did is we did a bunch of discharge tests. So this is just showing a couple of different C rates, but you can see for the fresh cell in the black, the capacity is much further over on the right. For the aged cell in the red, this capacity has shrunk considerably. The curve has moved to the left. And you can actually also see power fade because at 1C, going from the black to the red, you see a little drop in voltage. That's a small amount of power fade. And then at 4C, you actually see a significantly larger amount of power fade. That's caused that voltage to move downwards. So we can ask the question, does all this matter? We've looked at some cool graphs. Is this academic or is this practical? And I'll try to summarize at a high level what we found from our research so far. Basically, it's that if you account for only capacity fade in your state of health, if you don't look at power fade, you will typically overestimate the usable energy in your battery somewhere in the range of 1 to 10-ish%. And I say typical there because we tried to pick examples that are fairly common and normal applications, not fringe things. But if you go to really low C rate, that effect is going to be reduced significantly, maybe 1 to 2%. But if you start to go into high power or high age applications, maybe second life, you can really tilt the needle over 10%. So when I see something changing an energy number by something in the order of 5, 10, maybe 15%, I would say, that is something that we care about. If you're looking at a 100 megawatt hour site, it's quite a bit of energy. So we think that this is definitely worth looking at and worth caring about. Let's have a quick recap on what we learned today. So starting with the definition, we saw that state of health is about today's performance, not predicting the future. We also saw that while there's a myriad of degradation mechanisms, really you can link them all back to two major impacts on the battery performance. That's capacity fade and power fade. We saw that energy fade is a result of both capacity fade and power fade. And we also talked about how the degree of energy fade depends on the particular application. And that really affects how much energy you can pull out of a battery. A battery at the same quote unquote state of health in an amp hour sense may perform differently for different applications. So really we think that energy-based SOH is a better and more comprehensive metric to apply to energy storage systems when you need to think about end application performance. And I'd like to bring it back now finally to this idea of making better decisions. There's certainly a lot of different decisions we could make based on information. And what are two really tangible ones that could maybe help you out? First one, I think, will be a short-term decision, something that you do at the start of a design. And then a second one is really thinking out years down the road. So we think that if you're going to select the BMS for your battery, it's probably wise to look for one that has the ability to estimate both capacity and cell impedance. If you do this, you open yourself up to the world of really being able to do more comprehensive energy-based estimations of state of health and just get a better picture of what's going on in the battery. So if you need help finding a BMS that has such features, you can talk to us and we can help you find a Nuvation BMS. But we think a more future-looking or interesting application of this might be thought of through this thought experiment, where I'll ask the question, can I increase my battery state of health? And if you just think about state of health from the perspective of amp hours, the answer really is no, because if the battery has degraded and it has been left in a certain chemical state, there's really not much you can do to reverse that damage. That would certainly be very cool if we could do that. But if we shift our perspective and we look at it from the energy perspective, now how we use the battery actually becomes a more significant factor, and that can actually tilt the needle one way or another. So one application's 70% SOH might be another application's 80% SOH. And this is something you start to see in applications that maybe use second life or repurpose batteries, where you take something out from a higher power level or a certain topology and you repurpose it into something else. And now you actually are able to extend what that battery can do because the application is different. And we think that state of health should really follow that repurposing and reflect how the battery is used. So can you actually increase the SOH of a battery? Well, it depends, but from the right perspective, and if you consider energy in this, the answer is yes. So with that, thank you for your time. I just want to open it up for some questions and we'll do the best we can to answer them. And also joining me today is our CEO, Michael Worry. So we may tag team on some of these or just decide how to answer them depending on what the question is.